electronegativity. Electronegativity, ability of an atom to attract electrons, especially those electrons in a shared chemical bond. All right, electronegativity. So we went through all this yesterday. Like I said, electronegativities tend to increase as you go across a period. They tend to decrease as you go down a group. All right. Highest electronegativity is fluorine, 4.0. The lowest is 0, which is the noble gases, or the lowest for the metals is 0.7, which is francium. I showed you the difference between lithium and fluoride, and I said that fluorine's actually a smaller atom because there's 9 protons and 9 electrons, so there's more opposites attract, so it shrinks it down more, condenses it. Okay, so make sure you know that as you go across a period, the general trend is that the atomic size tends to decrease. Okay, atomic size, not the weight, the size. Okay, going down a group, of course, they have to increase because you're adding on more energy levels as you go. And then we get to, we did a little thing with the distance here thing, okay? And then we get to this here yesterday is kind of where we made you copy this down here. I said ionic bonds, and we know that is a metal and a non-metal here. So I drew this. I'm just going to draw it again here today just because I want to use these. You'd show me that, right? Arrow. And we'd end up with sodium ion and chloride ion. And I told you guys yesterday that maybe should look up the electronegativity. So you get your periodic tables out, right? And you say chlorine has a 3 somebody? Electronegativity, come on. 2? Okay. And this is 0.9. Okay? So if we look at the difference between those two, 3.2 and 0.9, it's quite substantial, okay, on a 0 to 4 scale, that is. 3.2 minus 0.9 is about 2.3, is the difference in electronegativity. Well, that's pretty strong. And basically what that means is that chlorine is strong enough to take that electron. It's not going to share it. It's just going to be strong enough, and it's just going to take that electron. And sodium's going to say, hey, you know what? I can't attract you very well anyway, so go ahead, take them, and we'll both be happy. Chlorine now becomes chloride, has 8 around it, so it's full. Sodium loses its 1 valence electron, it's full. So we're happy, we're good, okay? However, okay, so we look at that 2.3. Then we got to non-polar covalent bonds, and you guys wrote down the notes for this yesterday, and as well as polar. But let's take a look at non-polar covalent bonds. And things like N2, F2, Cl2, N2, etc., etc. What are these really? What's another name for N2, F2, Cl2? Well, actually, before that, let's stop for a second. What does this word mean to you? Covalent. What does covalent mean? When I say covalent, you say molecular. When I say covalent, you say sharing. I wasn't actually looking at you, but good, yeah. When I say molecular, you say, hey. It's like a rap. No, what did I say? Did I say covalent or molecular? Oh, okay. Anyway, covalent, sharing, yes. Covalent, molecular. Covalent, you say, when I say covalent, you say non-metals. Yes. All right. When I say hey, you say ho. Hey, ho. All right. That's fun for me. That's pretty much all the fun we're having. All right, so we're not going to do N2 because that's too messy. I'll do F2 again. So F2 instead. N2 works just as fine, but let's just keep it simple. F2, let's draw F2. Okay, so there's F2. Well, there's F, actually, sorry, that's just technically fluorine atoms. We haven't connected them together. So when I say covalent, you say sharing. I say sharing, you say covalent. However, fluorine, right, 7 valence electrons, looking to get another one, looking to share, yes? So this fluorine here wants those 2 electrons, yes, or those 2 in between the 2. Now remember, electrons are going around and around, so they're sharing, but simply put, if we're just drawing that, and that fluorine wants those 2. Here's the dealio, though. Guess what? They both have the same electronegativity. Okay? Fluorine, obviously a fluorine atom has electronegativity of 4.0, so it wants to attract electrons very well, actually, with a force. We're going to do a little bit of physics right now, and if you don't know physics, that's okay. We're going to do very, very simple physics. That's why I'm calling it physics. This is, if you can understand a tug-of-war, you can understand physics right now in this part. Okay? So, the left fluorine here, this one here, okay, this one here, wants to pull electrons this way in this shared chemical bond. Yes, its own, but the shared ones, with a force of 4.0. Wants to pull electrons towards it. Okay? Problem is, we have another fluorine here. And this fluorine here wants to pull those electrons with a force of 4.0 towards those 2. Those 2 electrons towards it. Okay? So the question becomes, with this simple physics problem, this tug-of-war problem, who wins? And the answer is, Zane, nobody. Nobody. Well, we're going to move on to the next one. We'll come back and we'll kind of compare and contrast these 2 here as we go. So sometimes it's better if you understand polar covalent bonds. But those 2 electrons are going to be shared equally. They're going to spend, those 2 electrons, or those valence electrons are going to spend equal amount of time around the left fluorine and equal amount of time around the right fluorine. Okay? They're going to be equal. It's going to be nice and symmetrical. It's going to look very nice and pretty. Okay? Polar covalent bonds. When we talk about polar covalent bonds, we talked about all this stuff here. It says there's one atom that has a higher electronegativity. It pulls electrons closer to it, etc., etc. We'll get to all that, I think. But let's take a look at what HCl looks like. HCl, of course, starts out like this. And when those 2 atoms get close enough together, okay, we can talk about electronegativities here. Electronegativity of chlorine was 3.2, and hydrogen was 2.2, yes? So when we look at the difference between that electronegativity, well, it's about 1, yes? So the difference here, if we take 3.2 minus 2.2, is 1.0. Okay. So, you know, comparing that to our first ionic one, the number's not a lot lower. The difference in electronegativity there is not that great. Okay. However, the question becomes, when I make this bond here, for example, okay, so when they actually do get close enough together, and I'm pulling with a force of 2.2 this way, and a force with 3.2 that way, once again, simple tug-of-war says, who's going to win in this case? Colin. Chlorine? Yeah. Chlorine's going to win out, right? So what happens is chlorine has a higher electronegativity, has a better ability to attract those electrons in a shared chemical bond. It pulls electrons towards it. And in fact, I'll show you another diagram that kind of exaggerates it a little bit, but it pulls electrons towards it. Well, if it's going to pull electrons towards it, by the way, here's the hydrogen thing here. Here's the chlorine. Okay? If we're thinking about the hydrogen valence electron and the chlorine one, they'd probably spend more time closer to this side here. Okay. Now electrons, of course, have what kind of charge? Yeah, negative. So if there's a negative that's spending more time on this atom here, it's going to gain a little bit of a charge. And not a full charge, just a little bit of a charge. And we represent that by putting a partial negative charge. That's that delta symbol that I had you guys write yesterday, or the music note for you bandies, okay? Whatever you want to do, okay? But because that electron gets pulled closer to chlorine, that electron's negative, it gains a little bit of a negative charge at that end of the molecule, or at that end of the compound. And if this basically has pulled that electron away from here, what's left over here? Well, there's a little bit of a positive charge left over here as a result. And the easiest way to do that is to figure out which one is the most electronegative and put a partial negative on that one. That leaves the other one with a partial positive. Okay? Always. Because remember, if you have one proton, look up here guys, if you have one proton and one electron, it's neutral, yes? And if you have chlorine's what, 17 protons and 17 electrons, it's neutral, yes? But if this one's spending, if this electron here, right there, is spending more time over here, what are you left with here? You're left with a little bit of a positive charge, yes? The nucleus, kind of, right? That electron's over here. So that's the negative end, and that's the positive end, okay? So you get kind of this, and that's exaggeration. Basically what I'm saying to you is the electrons will spend more time around the chlorine than they will the hydrogen, because chlorine has that ability to attract electrons better. All right? That's when you get this partial negative, partial positive charge. Are they still sharing electrons? Yes. Are they being shared equally? Absolutely not. Okay? So, right here I'll put not shared equally due to difference in En values. Okay? The higher electronegative atom, it's a fancy word, the higher one with the atom with the higher En value always is the partial negative. Okay? So electrons get pulled closer to chlorine. Chlorine gains a little bit of a negative charge. Hydrogen gains a little bit of positive charge. This is most certainly not an ionic compound. Okay? This is two nonmetals. They're still sharing. How do I know? Look at the difference between the two. 1.0. That's not a lot of difference between them. You might say, what's the magic number? Well, we're getting to there. Okay? And even after I tell you the magic number, it doesn't work for all of them. So it is what it is. But what you have to understand is that these are two nonmetals. They usually share. Okay? But they're not being shared equally. We go back to the top here. That's called polar. Why polar? Well, because you got a positive end and a negative end to this molecule. A little bit of a positive, a little bit of negative. Think about poles, north and south, opposite one another, positive, negative. Think about poles on a battery. You got a positive terminal and a negative terminal. Okay? On a 9-volt battery, they're right beside each other, sticking up. I just got some the other day here. So positive, negative, right? Think about poles, positive end, negative end. That's a polar, covalent, still sharing, okay, bond between the two. This one here, look, 4.0, 4.0, they're sharing equally. So there is no poles, which is a little bit of a lie for right now. There is no poles to this. It's neutral. Those two electrons are being shared equally. Okay? And they are. They still are later on too. But there's a little adaptation we'll do with that. Okay? So that's nonpolar because there is no positive negative end for right now. Okay? We're just simply talking about, and I don't want you to get too confused today, we're going to start nice and simple here. This is just a bond between two atoms. That's it. We're not talking about anything more than that. So look here. I'm talking about this bond right here, H to Cl bond. Okay? I'm talking about F to F bond here. Okay? In this particular case here, I'm talking about, yes, an ionic bond, but the bond between sodium and chlorine, which happens to be ionic, so I drew it like that. I'm only talking about the bond between two atoms, and I'm only focusing on those two atoms today. That's it. All right? Now, how are you going to determine bond types? Well, you take the larger number. We've done this already. Yep. Take the larger one, you minus the smaller one. So, okay. And it says here, use the chart to help determine the type of bond created. Don't worry about that for right now. If you look at potassium and fluorine, and if you look at where they are, potassium's over there, fluorine's over there, right? Basically opposite ends. I'm going to guess that that's probably ionic. If you take fluorine, which is 4.0, and you take potassium, which is 0.8, that's quite a bit of difference, okay? That's a 3.2 difference on a 0 to 4 scale. So we would classify that as ionic, okay? And once again, you don't know the magic number yet, and that's fine. But if you look at chlorine and carbon, actually, I'll show you this one. Potassium, because it doesn't hurt to draw this one. Okay? Once again, fluorine's so strong, it's not going to share. It's just going to take that electron from potassium, and it's going to create this kind of bond here, an ionic bond, okay, of opposites attract, plus and minus ions. Okay? No sharing, just takes. Yep. Oops. This one here, chlorine and carbon, if you do the electronegativities on this, not a whole lot different, really. Okay, 3.2 and 2.6, that's a 0.6 difference. So if you show me, I'm going to actually ask you to do this today. Okay, now I don't know, that's just a single bond there, that's fine. But the carbon to chlorine bond here, okay, is, well, sharing. How do I know? Well, 0.6 isn't a lot of difference, once again. They're both nonmetals, so they're probably sharing. Are they sharing equally? No. So we would classify this as polar. Yes, polar covalent. So this is most certainly polar covalent. I think it says that actually, but I'll write it down. And in fact, you should be able to look at this bond here, the bond between these two atoms, and tell me which one's the negative one and which one's the positive end of this bond so far. Which one's the negative end? Sure, Katie. Yeah, chlorine. And this would be your positive end there. Okay. Chlorine has the high electronegativity, so it gets the partial negative part. Okay. This is kind of important for later on here, because we're going to be doing a lot of polar, non-polar stuff. In fact, we're going to focus about 3 lessons solely on molecular compounds coming up here, and what strengths they have, et cetera, et cetera. So this is kind of important stuff here. You might say, okay, well, what's the magical number? How do I know it's ionic? What, you just say, telling me that? Well, they came up with this chart here, okay? And really, you don't have to memorize this number here, 3.3. The one that you maybe want to memorize is 1.7 here. But here's the deal, okay? When we talk about if the difference in electronegativity is between 3.3 and 1.7, so if you find 2 atoms and you subtract them, and if it's between those 2 numbers, you would say it's probably ionic. And I would probably, for the most part, I would probably agree, okay? And it tells you it's ionic there. If it's between 1.7 and 0.5, we classify that as polar covalent. So polar sharing, yes, nonmetals. And then if we get down to 0.5 to 0, it says that it's slightly polar covalent. Honestly, I don't care, okay? As far as I'm concerned, I would say that this whole thing up to 0 here is polar, okay? That's the only thing I would say, okay? I don't really care if it's slightly or if it's very polar covalent. I just want to know kind of where it fits into, okay? So anything above 1.7 we would classify as ionic. Anything below 1.7 we would classify as polar. If it's 0, it tells you at the bottom here. If it's 0, it's actually nonpolar. Well, when do you get 0? Think back to our examples. When do you get 0? What's the nonpolar ones? Yeah, that's the same on both sides, right? Like I have no bright or clever friends, yes? And those are called molecular, yeah, no. Everyone's yelling out answers, but no one's saying it confidently enough. Molecular elements. I have no bright or clever friends. People stupid? I have no molecular elements, yes? So when are you going to get the 0 one? When are you going to get the nonpolar bonds? Okay, once again, that's an important term here. We're focusing on just the atoms here, 2 atoms. When do you get nonpolar bonds? When the electronegativities are the same, when the atoms are the same. Okay? Now, does this work for all compounds? And the answer is no. So is there going to be ionic compounds that are down here, for example? And the answer is yes. Okay? Is there going to be polar covalent ones that are over on this side? And the answer is yes. Of course there is. So you really have to kind of go back to, for the most part, metals versus nonmetals. Okay? Where are those and what do they tend to behave like, right? But once again, the difference will tell you kind of how strong it is, how ionic it is, or maybe it's almost on the verge of sharing in some cases. Okay? And we're going to actually see that at the end of the units here. When we give you a little chart here, you might say, well, I think this is ionic compound, but it turns out it's probably more acting more like a molecular compound. Okay? There's probably a little bit more sharing there. All right? So I'm going to give you guys just a few to practice here. And let's see here. I want you to classify following compounds, or sorry, following bonds as ionic, let's say polar or nonpolar. I don't think I'm actually going to, I got first period to draw them, they got a little confused, so I don't think we're going to do that. Ionic, polar, or nonpolar. Let's do, let's put down electronegativity values and difference. And let's also put down the partial negatives and partial positive charges where applicable. So label partial positive, partial negative where applicable. Okay? I'll just get out of your way here for a second. Do we need partial positive, partial negative for ionic compounds? Yes or no? Do we need partial positives and partial negatives for ionic? No, right? Ionic is a full positive and a full negative, right? Is there a difference in electronegativity? Absolutely. But remember, that difference is so great that that electron is gone. That's what forms the full positive, full negative. These are slightly positive, slightly negative, okay? And also remember, polar covalent implies that it must be molecular compounds that we're talking about, or molecular bonds, okay? So let's give you a few. I'm just going to write down, I don't want you to draw them out, but I just wanted to write down 2 elements here, and I want you to see, classify them as the following here. And tell me which one would be partial positive, partial negative. Let's do C and O. Let's see. Oh, let's do, we did that one. K and O. KO. Knockout. Let's see. Oh, sulfur and chlorine. Well, that's probably enough for now, I think. Okay, so let's just do those 5 there. Hopefully that's okay there. All right, and I'll give you a little bit of time to work on those. Record this. C to O, Okay, I'm going to need some help with electronegativities here because I don't remember them very well sometimes. C to O. So what do we have to do here? Okay, polar, nonpolar, ionic, EN values, differences, label them. Okay, so this is what, let me get a different color here. 3.2, I think? No? 3.4. Okay. 2.6. Okay, so we can see that pretty close, okay, in electronegativities, not too far off. The difference here is 0.8. And if we had to label one, we'd put partial negative, partial positive, and of course this is polar, covalent. All right. So not that much of a difference, okay, if we were going to look at those two, yeah. I'm just going to call them polar from now on because we know that polar can only refer to covalent, right? K and O, geez, I don't even know. This obviously is 3.4. K is what? 0.8, okay? So we're looking at a difference there of what, about 2.6, and that's most certainly ionic. Very strong, pretty strong ionic. So ionic here, okay? We wouldn't put a partial negative, partial positive because remember, the K and the O, there would be that transfer of electrons. So there would be, the O would be taking electrons from potassium basically. Sulfur and chlorine, this is what, 3.2? What's sulfur? 2.6, okay? So the difference there is about 0.6-ish, okay? We do have two nonmetals there, so once again, 0.6. We're on the verge of very slightly polar covalent, but it doesn't really matter. There will be electrons that spend more time here, partial negative, than here, okay? So it will be slightly polar, but it's polar nonetheless, okay? So we would call that one a polar bond, okay? Now this one's a little bit tricky, and P and F here. This one's 4.0. Remember, F's really strong. It's really good at attracting electrons. P is what, 2.2, is it? So the difference there is actually 1.8. So you might say, well, geez, 1.8, that's a lot. That we should classify as ionic. And if we just had these two atoms, there would be a chance that there would be some ionic characteristics. So there might be some just taking and losing in this case here. We have to keep in mind that this is nonmetal, okay? So tends to be sharing. Would this share very nicely? And the answer is most certainly not. Fluorine would almost certainly try and grab those electrons if it could. I would still classify this as polar. I would say very polar, okay, on the verge of ionic. And here's the other thing we have to remember too, that when we talk about these bonds, that's one thing. But the reason I keep saying bonds is because we're just focusing on these two atoms, and I'm just trying to get you into the habit of which one's the negative one, which one's the positive one when we focus on a bond. But the problem is PF is not a, when we connect P and F together, they don't go together just like P and F, right? If we were going to do P and F, we'd probably draw this one here, PF3, right? So you'd be looking at something like this here with, right, like that, okay? There's 8 around each one, trust me. That's the machine gun approach. Well, there is. Well, there, you don't see the other one. It's right there, though. Okay. And then there's also, there's 8 there. That's good. And you don't see that one there. It was just right there. You didn't see it. So we usually tend to talk about these in terms of molecules and the big picture of things. Okay. And that's what we're getting to eventually. But right now, I'm just getting you to do that comparison so that you know. Okay. So in this scope here, these are most certainly going to be a molecular compound, okay? So it's going to lead itself to a molecular compound. That you just have to wait a few more days for, okay? So is it going to be ionic? Is that fluorine in fact going to take those electrons? And the answer is no, it's not, okay? You're going to see that stuff kind of balances each other out, especially in different shapes and things like that. So we'll talk about that as it comes up. Calcium and fluorine, though, that's a 4.0. Calcium's a what? 0. What? It's a 1? Okay, so the difference there is 3.0, of course. That's probably ionic. I would tend to believe it's ionic. It's metal, non-metal, right? Not really a shocker there. So that one's a little bit more easy to determine. People always freak out about this. What happens if you ask me that? What do you want me to put? I'm not going to ask you that, okay? I'm just trying to get you used to that in some cases there's a negative end and there's a positive end. Which ones are ionic? Is that ionic? Probably not. It's two non-metals. Is it on the verge of that? Yes, it is. It's getting close, okay? Do they actually steal electrons? Maybe they do, okay? But it's very, very close, and in the big scope of things, that's what we need to focus on, okay? We don't need to worry about these little, well, we do, but it's not as important, okay? So that's what we're going to do, over the next little bit here. So today we talked about molecular bonds, basically, well, and ionic, I guess, as well. So what we're going to do is we're going to jump back and forth. So it's important to keep in mind what we're doing each day, kind of thing. So today we looked at differences in electronegativity. We looked at ionic, polar covalent, and non-polar covalent. Okay. Tomorrow, for lesson 10, we're going to solely focus on ionic and what those look like. What is the structure? What is some of the properties of ionic compounds? Okay. And we're going to focus solely on that tomorrow to start with. If we have time, we will then move over to molecular and show you what do those structures look like. Okay, what are some of their properties? And we're going to go back and forth a little bit like that. And in fact, we'll talk maybe even a little bit about metallic down the road here as well again. Okay, so that's what we're going to do.